Dear viewers, you are my greatest inspiration. You have supported me all these years. Your kind words of appreciation motivate me to keep making more videos. In the early years of the 20th century, certain paradoxes and mysteries and quandaries emerged that the theories of Newtonian mechanics, electricity, magnetism, and thermodynamics were unable to resolve. Quantum mechanics developed through the attempts to account for these shortcomings of the classical theory. This was the dawn of fundamental transformation and paradigm shift. The framework of classical physics was unable to account for blackbody radiation, as well as several others, such as heat capacity of gases, atomic spectra, Compton scattering, light-matter interactions, and behavior of matter on the microscopic level, since classical predictions disagree with experiments. In this video chapter, we have succinctly pointed out the major contradictions between classical concepts and experimental observations. The viewers are advised to watch my previous video lessons, Photoelectric Effect, Blackbody Radiation, Wave-particle dualism, Compton scattering, Newtonian mechanics, and electromagnetism, prior to this video. Planck's constant, h, has become emblem of modern physics. Limitations and inabilities of classical theories, particularly at the atomic and subatomic levels, ultimately demolished the foundations of classical physics. Historic contributions of the legendary pioneers, Max Planck, Albert Einstein, Niels Bohr, Louis de Broglie, and Arthur Compton, have been extensively discussed in numerous chapters of my comprehensive video lectures. So, how the classical statistics failed to explain photoelectric effect? Curious? Keep watching. When very dim light shines on a metal surface, it isn't really expected to eject electrons immediately, right? But it does. Experiments show that if light of a certain frequency can eject electrons from a metal, it makes no difference how dim the light is or how intense the light is. There is never a time delay. Taking into account that classical physics proposes undulatory theory of light, let's have a brief overview of the conceptual concerns and contradictions with respect to the following key topics. Classical belief of continuous wave and continuous energy distribution across the wavefront does not account for the quantization of light, which is crucial for explaining the photoelectric effect. In my earlier videos on my channel, you have already learned the experimental facts of blackbody radiation. The blackbody spectrum depends only on the temperature of the object, not on what it is made of. Well, all objects emit the same blackbody spectrum if their temperatures are the same. In the illustration, we can see that the energy of blackbody radiation is not evenly shared at all wavelengths of light. As the temperature of an object increases, it emits more energy at all wavelengths. That is to say, the total amount of energy radiated by the object increases with temperature. As the temperature of the object increases, the blackbody radiation spectrum shifts towards shorter wavelengths and diminishes at the left-hand side, which is the high-frequency side. In my earlier videos, you have also learned the fundamental science behind heat and light. The intriguing interplay between heat and light. As the temperature of an object increases, the peak wavelength of the blackbody spectrum becomes shorter, more blue, to be specific. Well, so, blue stars are hotter than red stars. For a quick reference, please watch my video lecture Color versus Temperature one more time. Okay. Rule of thumb. Owing to atoms in constant motion and collision within all objects, the hotter the matter, the more intense is the motion, and the more frequent are the collisions. And brighter they glow. Now, let's look back at the explanation of classical physics relating to vibration of electric charges, light emission as electromagnetic wave, and heat as the kinetic energy of random motion. Nonetheless, classical physics failed to explain the shape of the blackbody spectrum. According to classical predictions, there is no limit to the energy of the vibrating electrons at high frequencies, so to say. No, that's wrong. Why is that? The high-frequency end is marked by dotted yellow circle. Max Planck's proposal of the concept of quanta resolved this blackbody radiation paradox. In the concept of blackbody radiation, the phenomenon of the transition of color from red to blue, as an object is heated to higher temperatures, is not merely theoretical. Needless to say, it has tremendously remarkable practical relevance in thermal physics and climate science, analyzing heat distribution and energy efficiency. Classical predictions had a major setback concerning stability. For instance, electrons orbiting the nucleus in an atom would radiate energy, would eventually spiral down into the nucleus, leading to a collapse. Let's use the analogy to comprehend the resemblance, the orbits, and the electrical attraction, and the gravitational force. the orbiting electron would be losing energy continuously, and ultimately spiral down into the proton. Nope. That does not happen. Why and how? Instead of a continuous spectrum, atoms were observed to emit specific wavelengths of light. Classical models were unable to account for the discrete spectral lines emitted by atoms. It was not possible to predict by applying classical electromagnetism.
All right, anyway. Please remember to like, subscribe, share.